Yeah. Okay, good afternoon. So when Dr. Zheng Yu actually sent me email say I should give a talk in, this KDD in China. The first reaction is I'm not really doing anything for KDD in China. Actually, it's outside of China. So how can I talk about it? And but he says, as long as you get something people are interested in this forum, that should be fine. One link, of course, I can make is this is most of this research was done by the people originally came from China. Okay, so that probably can have some link. Okay. So since even you look at the picture, the background, the map actually is the U.S., Mexico, and Canada, because you see the Florida, it's that angle. So I just got a NASA map, just cut it and made it. Okay. So I just want to say a little work in the last 2 years. What we did, we think is exciting, and it may impact a lot of research. We can do. Of course, we got lots of students doing many things, but one thing I think is really may have some interesting impact could be we are doing data mining. The data mining, we want to get the data to knowledge. The data is big, but where's the big data? Actually, the big data, the majority of big data is on the text form, right? If you think about it, you get internet, you get emails, you get research literature, you get newspapers, all these are from text data, right? So you probably know we got Professor Yizhou San. She actually recently joined UCLA. She did amazing work on turning the network data into knowledge. But there's one big question is where the network come from, okay? The network actually, if you really say it's not coming from, people already structured network like DBRP, you have to get it from text as well, okay? So that's the motivation, okay? So what the first argument is we say we got a big data, but big data actually 80% is from text and natural language, social media, okay? They are not structured, and we want to turn them into structured. So we get 3 keywords. It's much worse than what Yu Zheng actually just told me, the 3 BMW. That's much easier to remember, okay? But my 3 keywords is one called structuring, another called networking, the third one is mining. Okay, it simply says we want to turn the unstructured data into structures. Then we can build up networks, then we can do mining. Okay, this is not like BMW, but it's still interesting enough for you to remember, okay? So if you look at the picture actually was done by Fangbo et al. He likes to show some global pictures. I really like it. We got huge amount of text data, right? And we got, say, knowledge base, like a Wikipedia, like Freebase, all these things. These things are easy to get. Actually, we have nothing secret because the data getting in is very public. Okay, data getting out is also very public. Plus, even the software is public. We actually got all those software is open source. So it's a contradictory to say nothing to disclose. We have nothing to hide. Okay. But I think it's interesting. You probably can see is we got the data. The first important thing is we got structures. Okay. Get structure, what we did is we get key phrases, that means phrase mining. And we get typed entities, that means the typing. And we get other structures. I'm going to show you some new progress on this. And it's going to reach to automatically construct the heterogeneous networks. Then we can get knowledge out of it. Okay, so that's a picture. Now, I'm going to discuss with you a few things. Actually, the only thing we should hide is the very last work, because we just submitted it. It's not published yet. So I will not disclose too much, because once it's published, everything is public. Okay, but all the other things are published. I probably can say a lot. So the first important thing is, if you go to NLP, go to machine learning, go to many other communities, you say, we need a lot of training, okay? But getting into data mining community, we say, we don't need a lot of training. We want a lot of data to mine. So we get big data, we get a smaller training, smaller experts, and when we can get knowledge, also big knowledge out. What's the magic we can do this? The first important thing we did is phrase mining. This actually, all the papers were published actually just last year, 2015. But actually, we are even working one we expect to get into 2017 because it's not quite finished yet. But it's very exciting. Okay, what is phrase mining? The phrase mining is you get lots of data, actually including Chinese as well, if you think about this. You get lots of data. You want to get phrases. Like Chinese is extremely hard. The reason is there's no gap even between words. Okay, so that's probably most difficult language you can imagine, right? So for phrase mining, the key is you get a large raw corpus. You finally want to get those phrases, like information networks or data mining or those things, automatically without anybody trained. Can we do this? Okay. Then if we can do this, then we can actually even go back to the document to mark those are the phrases, and this phrase will turn into the types or something. We can do really good mining. Okay. The interesting thing is we first got a top mine. This one was not done by Chinese, was done by Ahmed Erkishki in my group. He grew up in the US. Okay, but there are quite a few other co-authors are Chinese. But the sec phrase was done exclusively by the 4 Chinese, I should say. But these 2 papers, especially the second one, actually in the same month won the grand prize for Yelp Dataset Challenge in 2015. Okay, so why they give this grand prize? We did not get anything. They give us a big check. Okay, why? Actually, we did not even contribute a software to this company, to Yelp. Why this is so interesting? I just give you a simple example. You probably get convinced. You got lots of things, in the text. You want to find something meaningful. For example, you want to find support vector machine. Actually, it's a phrase. Suppose it came from Mars. How could you know support vector machine is a phrase in this text? It's very hard. Okay, but you get one title, you get nothing you can get. Okay, but if you get 2 million titles in DBLP, you will think the Martian is going to train by just reading 2,000 articles. Okay, so they may find some statistic correlation. You probably can find, say, support vector getting together is much frequent than they separately random getting together. Okay, and how frequent it is? If you think about a Gaussian, this typical Gaussian distribution curve, if they are 3 standard deviation away, the chance is 0.3% already. What about this one is 12 standard deviation away? It definitely should glue together. They should be a phrase. So you don't need anybody trained. You actually can get those phrases in a very, very high quality out. Of course, you need to get some false positives by going back to do the phraser segmentation in the text. Okay. But anyway, once you get this, you can use some simple heuristics like popularity, concordance, informativeness, completeness. I probably can explain. Informativeness means you don't want to get stop words. In a phrase, you don't want to get stop phrase. What is stop phrase? It's just like a meaningful, like of, is, and, or something. So you get phrases like this paper, you can rule them out because it's almost in any paper you have this paper, right? So, but like a vector machine, you can get a support vector machine. If every time vector machine comes, support vector machine also comes. The support vector machine is a real phrase, right? So you think this way. Actually, Erkishki, he got this, he feed his software into his little revised topic model. He got those very, very nice topics already without anybody trained. And the method, just because it's just like a frequent pattern mining, it's very fast. He mined like 200, those page documents. Getting those phrases, it takes less than 2 seconds, okay, to get those phrases. Actually, the majority of the time, actually, for mining, these things are on the topic model rather than the phrase mining, okay? And if you add more, like a human give a small number of labels, how many labels you really need? Jiawei actually did this test is you just need 300 labels, like positive and negative, those 300 labels on the phrases. You get gigabytes. like documents, you will take, you will get a very high quality already. It's a very small number of training data. But you can construct a good classifier using random forest or something like that. And the result actually is very interesting is he mined all the KDD titles, tried to get phrases. You probably can see he tried the Stanford, those kind of a name chunker, okay, those kind of name entity chunking. You can see that they got many stop phrases. For example, important problem, effective way, small sets. Those are almost any paper. Not in data mining, you will get it. But he can get a lot of these red ones, they did not show up in name chunking like time series, gene expression data, frequent subgraphs, those things. You can see it's a very interesting. Another interesting thing is because these things essentially based on statistics. And he went down to the Chinese called Baidu Baike, those Wikipedia in Chinese. He actually mined this, you probably can see these are the, even you mine to like 9,000, this ranking, you still get very good phrases. Like those, 国家戏剧院, those things, you probably can see. This is pretty good phrases you can get. And Erkishki tried on Arabic, it works fine. We tried on Spanish, works fine. The interesting thing is once we publish software on the web, there are some company, they notice it. One company is TripAdvisor. They grab this and they first do the phrase mining, then do a little embedding, then finally find it's so good, it beat all the software. They actually come back to us. They say they want to work together with us to not just for Chinese or Arabic or English. They want to get 10 other languages because the TripAdvisor needs many, many languages to mine the phrases. And Jingbo said, oh, instead of working with them, we just can't do it by ourselves. So far, he already worked very nicely for all Latin-based language. He can mine the phrases in a very high quality already, okay? And then another interesting thing is typing. Typing means not only you get phrases, you want to get those phrases, also get the right types. Suppose it came from Mars. How do you know this barbecue, BBQ, is a food, okay? And how do you know Phoenix is not a bird, but is a city, it's a location, okay? So, of course, it's very hard. We cannot say we do not need any training. We do need something came from the general knowledge base, like a Wikipedia. We actually use Freebase. But the problem is for Freebase, the first problem is it's sparse links. You're just thinking about it, you get a Twist, you get a Yerp. Majority of them, you go back to the Freebase, you cannot find the entries. Okay. The linkable one, we actually got a statistics, it's only 7%, 93% not linkable. Okay. Since they are not linkable, how we can get them? Another thing is, even it's linkable, it's ambiguous. Just to give you a simple example. You look at Washington. Washington could be a state, could be a city, could represent the US government. Actually here, like this one, Washington's plan on Sunday's game actually is a sport game because it's in Washington. Their sport team actually is something like a Washington beats Boston. Actually, it's not a Washington, the city beats Boston as a city. It's two sport teams, right? So how can we know at this point Washington is a sport team, okay? So of course you can say people do training. Remember, you get 100,000 of things. Who will give you labels, right? You have to do it by yourself. Okay. So to do this automatically, which is very hard, what we do is taking Freebase, okay, taking this, the documents, we do the distance training, then do the information propagation back and forth, doing relation phrase clustering. The details with the time, I will not give you the details, but I'll give you general ideas. The general idea is, you take the cases, you construct the graphs with mentioning, relation mentioning, with entity mention, with relation phrase, you link in a structured way. That means whether this one appear in the front or appear afterwards, you actually give different colors, different labels, and you think about this. You use one phrase, you can construct this. Now you have hundreds, thousands of phrases. The graph you constructed is massive, but anything originally in the phrase base you can propagate. Now you can propagate back and forth in many ways. You can mutually enhance them. Okay, so the whole thing is a mutual enhancement framework built in the whole optimization framework. Okay, you can think of optimization with constraints. So we use type propagation in these heterogeneous graphs with multi-relation phrase clustering. Okay, so these propagate back and forth. It becomes really powerful. I can show you is last year I could give a talk in Beijing is ACL 2015. They asked me to give a keynote speech. I was a little afraid because I've never been to any conference in natural language processing, and this is the top one. But we show, the interesting thing is, Xiang actually showed this one. These are also our most famous NLP software. Some were done by Stanford, some done by University of Washington, like Figer. These are all the very top team internationally. And this one was done by Xiang Ren. Okay, so you probably can see, this is New York Times with 300,000 articles. This is Yelp, the other one's tweets. Those are the real large amount of real data sets. And we show the precision recall in F1. You probably can see this F1 comparing to the previous known software. Actually, the F1 is far higher. It's not just a little higher. Okay, so it was really shaking the NLP people. Actually, they come back to discuss with us, say, what happened? Okay. Actually, the interesting thing is we have very different philosophy because we are data miners. Okay, the data miner is not as deep as NLP people can get into every sentence. If you just give me one sentence, you ask me to give all these types, I'm dead. I definitely will say, no, I cannot do it. But now we have hundreds, thousands of documents. They can do all the correlation mining, all the linking, all the propagation. With this, we got the real power. Okay, the big data got the real power. Okay, that's one. Actually, one guy in the ACR platform, he actually raised a question. He said, what is your philosophy? How could you beat our so many years of research? I just say, I do not really have anything super smart. You just think about this. Suppose we got one very smart American journalist, okay, knows only English, but was captured by Taliban. Okay, Taliban put him in the cell, only give him newspaper in Afghanistan, which is Darcy. Okay, suppose the first day he reads this newspaper in Darcy, there's nothing making sense, right? But if he was locked there for a year and he's smart enough, he wants to learn, he can do all the correlation, reading this, thinking this, mapping with the picture. After a year, he probably can read the newspaper, the majority of them. Okay, you can think about this. This is possible, right? That's the power of this correlation, this massive data. Give me one newspaper, I'm dead. But give me 1,000, I could be alive. Okay, so that's the general idea, and actually it works. Okay. The detailed one, there's another very interesting one. I would suggest you to go to Xiang's, Tuesday evening, the poster. Okay, I really like his work, but his work put it into a poster. But you can read it. That one is go one step deeper than this. It's trying to find a very refined type. This one, actually, the game is finding like a time, region, location, organization, event. Those are the high-level types. And his new work in 2016 was going down, for example, Trump. You can find Trump is a person. That's nothing magic. But do you know Trump sometimes is a politician, like a presidential candidate, but sometimes it's a businessman. But sometimes actually it's an actor in the reality show, right? So in this sentence, do you know Trump is an actor or he's a politician? Okay, so of course you may say he's both, right? That's just a joke. But anyway, if you really can automatically identify this, the problem is you look at the training data. Training data itself give you multiple labels. They are noisy. Okay. If the training data cannot give you the unique label, but give you many labels, you finally want to get the right one uniquely. Okay, get the right one. It's not easy. And he basically show you how to do it. Okay, you probably want to go to talk to him. I do not know whether Xiang is here. Okay, he may be in some other sessions. Okay. Yeah, but I probably can say one thing is Xiang this year, 2016, for Google, Google give the Google PhD scholarship, PhD fellowship for a year. He probably give like 15 or 20. This year for structured data, for North America, Europe, and the Middle East, the 3 regions, they only give 1, and they give it to Xiang. Okay. So it simply says Google really like his work. Okay. Now we get into relationship discovery by network embedding. Okay. Relationship discovery means not only you want to do embedding, you want to find the entities and the types, you actually want to find the relationships between different entities. To do this relationship mining, you do need some networks because so-called relationship are the links. Okay. So we actually took Microsoft research, Jian Tang. I do not know whether Jian Tang is here, but anyway, Jian Tang, he published one paper in last year, WWW 2015, and another one, actually I was a chair session in Australia, in Sydney, that was in KDD 2015, okay. We took his paper line, okay. Then we, based on phrase mining, we actually mine very large corpus to find their relationships. Just give you a simple example. This essentially is just based on embedding. Okay, you calculate the vector embedding space and you calculate their differences. You can use those arguments to calculate the other ones. The detail I'm not going to give you, but I just give you the general philosophy. We randomly took 10% of PubMed abstract data. Okay, you know PubMed has 30 million papers. We randomly pick up 10% abstracts. Then we detect using those phrase lists, using our phrase mining and using their some phrases as well. And we try to find co-occurrences. But I just give you some example, you probably find it's quite interesting, is we just need one query pair, okay, just to say, or you can say sample pair, the seed. We took breast cancer and BRCA1. BRCA1 is a gene name. If you know bioinformatics, BRCA1 actually is a breast cancer 1, sort of using this one, name this gene, okay? So you take breast cancer and BRCA1. That's a pair, means this is the disease, this is a very close related gene name, okay? So now we can give the query, say, now I want to find this leukemia. Leukemia is a blood cancer, right? So you want to find acute myeloid leukemia. What are the most related genes, okay? And with mining those abstracts, you actually can get a ranked list of the genes or proteins related to this particular disease. And this one, actually, for example, you get a leukemia, this is the drug, okay? You can say this is the drug, you want to find it from the drug to the disease or from disease to drug. Then we may say, oh, this guy got a small cell cancer, what are likely the drugs? So you will find likely drugs. So this is pretty amazing use. Phrase mining plus those embedding. Actually, Meng Qi, he went back to Microsoft Asia in the summer. He further refined the line algorithm. He used his heterogeneous information network, integrated with this embedding. And he found, he can do this one even better. Okay, but that's a result he got in the previous one. But the very last one I want to show actually was Meng Jiang's work. Is Meng here? Meng is not here. He probably in the other session. Okay. But anyway, this one I probably should hide something because we just submitted. We haven't got it accepted yet. But I probably can show you this is what Google has been doing, okay? What Google doing this year, in 2016, they published an amazing paper, is this, okay? What they do is, they got very big data. They want to automatically find, giving me entity, for example, person. I want to find many of their attribute names. Okay, for example, you get a person, you want to find a wife, you want to find daughter, you want to find daughter's dog, all these things, you actually can, how many you will get, okay? So what they show is they got like one country. They find the number of attribute name they found is over 100,000. The accuracy is over 90%, okay? So that's what they're constructing their Google knowledge graph. That's what they're doing, okay? But Google has one unique feature is they collect huge web logs. And web logs actually may say Obama's daughter's pet, okay? Then that actually means there's an attribute called Obama is a president, president of the US country, you actually can get a country's president's daughter's pet. Then that's one attribute you can get. Okay, you can get this kind of thing, you can get 100,000. But the problem is normally we will not be able to get web logs. Okay, we don't have query logs. So we don't have query logs, we want to do the same thing. And we actually want to do it in a very precise way, not only get attribute, but also get attribute values, okay? So I discussed with Meng. Meng actually got a PhD in Tsinghua University. Last year, he got the dissertation award in Tsinghua. And he also worked with Christos, and he got a very strong recommendation from our crowd. I get him to my group, and we got a substantial discussion, especially after in the spring, I visited Google. I found their approach is so exciting. I came back to Meng and say, we need to do something, even we do not have any web log. We don't have query logs. Then we found, actually in the summer, we found that we actually can use, there's a Google project called Biperpedia, and we actually got a Metapad, guided the attribute discovery. That's why we call it Metapad. For this Metapad software, I can show you, these are from the corpus is the real newspaper. What you can see, you can get for example, you can get Pearl Harbor, okay? The Pearl Harbor, of course, is one attribute, this is one entity. The attribute value we link is December 7th, 1941. You probably know that's a Japan actually bombed Pearl Harbor, that's the exact day, okay? Then we get a Beijing, we got October 11, 2013. Actually was, there's one called Beijing has a UCI World Tour of Beijing, that's a particular day. Of course, in that newspaper, you grab it, you find the exactly value associated with this. For example, you can find, Romania's prime minister or Egyptian's prime minister without anybody trained, without anything. Okay, you just go down the newspaper, you get this pattern, you will actually find tens of precise value pairs, much more powerful than the slot filling in natural language. Okay, so that's the power of big data. Okay, we really got amazed we can get this. So that's why we got excited with our data mining approach. Actually, the big data, we probably can do something pretty magic. Okay. So now I probably finally give you the conclusion is we say the data actually is everywhere you get a large text, you actually need to mine the structures, construct networks to do data mining. And with some big data, you really get a big advantage for us to, to do something pretty exciting and magic. Okay, so this one I just show you, even for my own research, we start from general data mining, we get into link mining, then this is Yizhou Sense mining heterogeneous information network, got the KDD dissertation award. Then Chi Wang's mining latent entity structures, got last year's dissertation award. So that implies For data mining, instead of mining general data, you really finally get into the most massive data, which is the text, unstructured, and you want to turn them into structures. Okay, so that's the research, and unfortunately or fortunately, we did not get any Chinese name, but we got enough money already. Okay, so those are the recent publications. If you're interested, you can go down to download it. Except the last paper I said is this one, submit to publication. All the others are published, and most of them actually is open source. You can download from the first author's website. Okay, you go down to their GitHub. Thank you.